life gets too much in the way. Like right now.
Yeah.
Legal troubles.
Okay. I don't have 5 of you guys, but as mechanics is recorded, so it should be fine. Okay. I got a solution. I probably, you guys already watched the video over there. I eventually figured things out, and I think we just spend the time. I'm going to explain the details in the lecture, and we'll do the lab today, and we'll just finish it up. After today, we shouldn't spend a significant amount of time on this project anymore. So at least either 80% or 100% of the project should be done after the end of today. Keep that in mind, okay? It's doable. So the strategy is using a leader transmitter instead of follower transmitter. So the IPGA becomes the leader and the transmitter. So Arduino SPI won't be used anymore. Instead, we are writing a soft SPI, and this will happen a lot in the industry or in the practical projects. So a lot of times the digital module in the microcontroller is not really compatible with your peripherals, and you just have to write a soft digital module of it. I'm going to show you how to do it. But for this one, just look at the timing, and by looking at the timing, you program a C code to implement it instead of using a digital circuit which receives a pulse or digital signal and respond with a certain digital signal. It's the same thing. The results will be the same. We just write it up or implement it using C instead of hardware in the microcontroller. Okay, so we are bypassing that SPI module inside the microcontroller, and instead we are writing a soft SPI. Okay, so this IPGA now is being used as leader transmitter. Keep that in mind. It's going to be the different module instead of the follower transmitter we have used. It's going to be a leader transmitter, and leader transmitter has 3 different ports. So 3 ports are being used. So leader transmitter, think about that. What are the 3 ports? SPI. What are the 3 ports? So ICK at least, right? The clock, you need a clock. And second, enable. And third, MOSI, missile, which one? MOSI, right? So leader transmitter, leader is sending out, and follower is receiving input for the follower. Okay, so we need these 3 ports. You can see these are the 3 ports being used. I think these are at JB, okay, JB's ports. MOSI, SS, ICK, 3 ports. And I have to pick up 3 digital pins from the Arduino to receive these signals. And you can tell that there's no level shifter in the middle. It's because IPGA, which is a low voltage device, 3-point servos, is not receiving any input. So it's a 3.3 volts to 5. Okay? Which means all the ports on the Arduino are inputs, and all the ports on the IPGA are outputs. So which means they're not receiving any 5 volts logic. It's only outputting 0 to 3.3 volts to Arduinos, which is fine because Arduino can take up to 5 volts, and IPGA is outputting 3.3 volts at the most. Okay, so the Arduino will be fine, and the IPGA will be fine as well because Arduino is not sending out anything. It's only receiving. These are only inputs. So IPGA will be fine as well. It won't be damaged by 5 volts logic. So in that case, we don't need a level shifter anymore. Okay, it's just one direction. It's not bidirectional communication. It's one direction. All right. And I have another pin here, pin 11. So pin 11 is being used as a testing pin. I'm going to show you why it's so handy, and we're going to use this a lot. We're going to use this a lot in the microcontroller class in the fall. And also there are a lot of other technologies I put in Arduino will be taught in the fall as well. So these are just so important. That's why I think we should really go through this in details. Okay, so the hardware connection is pretty simple. I don't believe I have missed anything. 3 digital pins, and this one, so 3 over here, and this is a testing pin. The testing pin is just sending out the signal to the oscilloscope. It's not communicating with anything. I'm going to show you why I have to do this, all right? So on the breadboard, 3.3 volts connect to the right rail over here, and that 3.3 volts is being used for your amplifier board as well. Okay, just to be clear on this. So this afternoon we built this circuit, we show the results, and we are done with the project. There won't be any presentations. That's it. So one lab, by the end of today, we should be done. Okay, to reduce the stress of you guys. Just have a few days left for the week. So you just need to solder this circuit, follow the instructions, solder it, do the connections, and program it and repeat the work, and show the results eventually. Okay. And for the hardware connection, you have an amplifier. Amplifier has a VCC, which is 3.3 volts. Remember the power supply for the op-amps, right? 3.3 volts. You need a 3.3 volts, and IPGA has that 3.3 volts available. Then just use it, okay? Which is over here, connect to the power rail and ground to the ground rail. So we're using this breadboard as a like wire hub, right? A hub, making all the connections to the ground and VCC. And all the other ports should be grounded, and port 1, the differential input, one shorted to ground, another one shorted to V out of the amplifier. This amplifier generates a voltage, analog voltage output, instead of your heartbeat pulses. The photodiode, for some reason, I just used so many different ways trying to get signal out of it. It doesn't output anything. I still don't know how to figure out the problem. It's not a really popular device. I couldn't find any examples except the one I posted to the website. That's the only one used that module. I separate and connect the power supply, and still no response. I use a flashlight directly, shines on the top of it, still no response. I don't know why. So I just gave up. I'm not going to use that sensor anymore, which is fine, you know. We can just modify and still get something out. So I removed, because we are not using that IR photodiode, so we don't need that IR emitter as well. So I removed this guy. I removed this guy as well, and also the 1 mega ohm resistor at the bottom. I removed it to improve the gain a little bit. So I'm connecting a photodiode, but in the visible range. Okay, it's not IR anymore. It's a visible range. In the visible range, and this photodiode is shorted to the 2 terminals to replace that IR photodiode. So keep in mind the short one is a cathode, so put a short one on the top and longer one on the bottom. Okay, and this one need to be changed as well, because the package I found on Eagle PCB doesn't really match with the footprint of the Zener diode. However, Alex and we were able to figure something out. So this should be, according to the footprint, this should be aligned to this pad, and this should be here, and this should be here. Okay, but that's not really connecting the right pins to the right traces. So eventually, we have to rotate it this way. So the middle pin on the top of the chip is not connected to anything inside the chip, so we don't have to worry about that. Even though this one is being placed on the top of this pad, and this pad is shorted to somewhere, we don't really use it, which is fine. So don't worry about the top pin over here, because it's not connecting anywhere inside the chip. So the only 2 ports are being used for the chip are these 2 ports. So this one shorted to this pad, solder it, and this one shorted to this pad and solder it. Apply some flux and solder it carefully, and it should be fine. We are running out of these op-amps, I think, but you guys already soldered somewhere else, either on the PCBs or on the adapter. I told you to do that, right, previously. So you have to unsolder it and put it back onto the PCB this afternoon. Hopefully we still have enough good op-amps to use. Otherwise, I'm gonna let you guys use mine. I mean, we should be able to figure something out, right? There are only 1, 2, 3. Only 4 groups. So I only need 8 op-amps. Should be able to figure that out. So these are the capacitors and resistors. So the way to do that is, at the very beginning, right, you use the syringe of the flux, and you put the flux on the top of the pads. For every single pad, you need to apply flux on it. And then you use the tweezer to grab the components, because the flux is sticky, right? So it's able to keep the components on the correct spot. And then you just place every single one on the PCB. And eventually, when you're done, you grab the PCB to the soldering station and do the soldering. That will probably take you probably I don't know, 30 minutes to 1 hour this afternoon to finish up the soldering. And after that, things will be easy. Okay, we make the connections to here, and then you synthesize the Verilog code. And also the Arduino code as well. I'm going to explain this to you really soon. And then connect all the outputs, the ports to the oscilloscope. Show a diagram like this of the SPI timing. And then have several snapshots of the output. Then we're done. Okay? So basically, I already did this project for you guys. 5-star service. Okay? Don't want to disappoint you. What's that?
I don't know. I just have to modify this board, right? Because it's already populated.
Is that the same design?
Yeah, it's the same
V1,
one.
right? Yeah. Just modify. Just rotate it and
get rid of the photo.
get rid of the parts. Yeah.
And the mega ohm resistors now?
Yes. Yeah.
I'll just
Should
do
be a
that.
very simple case for you. Yeah. What else? Okay, here. This is a clamping. It's called clamping circuit. I think we talk about this for the ESC protection diodes in VLSI. So what's happening is whenever this voltage is higher than, let's say, 0.6 volts, and this diode is getting forward biased, and it's gonna send all the current through the diode ground. Eventually, the voltage here is not really won't be higher than 0.6 volts, ideally. Okay. So why is that? Because the IPGA input is only taking up to 1 volt. We really don't want anything higher than 1 volt. I mean, whenever it's getting closer to 1 volt, I'm getting anxious. And so we are using ground. I mean, you can change the ground voltage here to like 0.4 volts, okay? Because the diode will internally drop at 0.6 volts because of the building voltage. And whenever this one getting forward biased, if you add a let me draw it here for you.
Oh, it's a voltage difference.
If you have a 0.4 volts, because this one will internally drop at 0.6 volts because of the silicon physics, okay? So whenever this one got forward biased, you got current flows in here, so the minimum voltage here should be 1 volt. But whenever it's higher than 1 volt, like 1.2 volts, it won't keep increasing. It's because of this one is internal drop, building voltage is permanent, and this voltage source is 0.4 volts fixed. So eventually it's adding together, it's just 1 volt. So it's going to stabilize this voltage at 1 volt. Whenever it's getting some surges, it will pull it back. However, when I was looking, I'm using the benchtop power supply, right? I'm creating like channel 2, 0.4 volts. And whenever this one is getting higher, because the surge, we have to put a flashlight on the top of the photodiode, and you can see the reading here is changing, it's increasing for some reason. So it's probably because I don't know what's really happening. We can maybe use a different reference voltage to make this 0.4 volts stable, but this is not stable. This is not staying at 0.4 volts. Okay, so that is why when I was connecting 0.4 volts, and whenever there's a surge here, this one is higher than 1 volt. So I got a little bit concerning here. So eventually I removed that 0.4 volts and directly grounded. It's a very solid ground. So eventually this voltage won't be higher than 0.6 or 0.7 volts. Okay? Just keep it safe. That is why we connected the regular diode from the output to the ground. Okay, so it's never So the voltage here is getting clamped at a lower of 1 volt or no 0.6 or 0.7 volts or lower. And okay, so now let's get into the software side of things. So after that IPGA piece or part is getting synthesized, the first thing you want to do is probe the ports. That makes sense, right? The IPGA is now being used as a leader transmitter. So in that case, it's sending things out. So that is why you want to see if it's really sending the correct data. You know, working on a project like this, you should always take baby steps and separate different problems. You have ADC and you have SPI, right? You want to directly connect them together and see if you're getting the good results. Or maybe you can do that, try if you are lucky enough, which is fine. I usually do that. Just want to give a shot and see if that works. But 80% of the time, it won't work, okay? It's really normal. Don't get frustrated. So whenever you see issues, you separate them again, and by looking at either ADC or SPI. So because I'm trying to observe the output from the SPI, so I didn't use any output from the XADC for the SPI. I just directly send a constant to it. How do I do that? It should be really simple, right? It's over here. See? That's in the top module of the design. Remember, I told you to use the little latch in the middle. We should still use that. It's a good practice. Data latch is a register type in the middle. So it's in the middle of the SPI and XADC. I just add another layer in there. So I'm not directly connecting the data out from ADC to the data input of that SPI. I'm adding a latch. It's actually an 8-bit flip-flop in the middle. So it's waiting for a signal from the SPI. When SPI is done, I send that busy signal here to the latch. So it's moving everything to the other side of the D flip-flop. Keep that in mind. It's very important. Okay, so that is why I'm doing this. I can come back and explain this later. Just don't worry about that. Okay, since it's been a while, and you can see, I keep updating it. So whenever it's ready, I'm sending the 8-bit data from the XADC to the data latch, which is the 8-bit flip-flop. Okay, and but for testing the SPI, I commented this out. So I'm not sending any XADC output to the data latch, which is the input of the SPI. So instead, I'm directly sending 00001111 to the input of the SPI. Constant. So what's happening is the SPI is taking an 8-bit constant and converts the parallel digital data into serial communication to MOSI. Okay? That's what's happening. So you are expecting what? 4 zeros and 4 ones.
Becomes a pulse. Right?
Always. Yeah, it's a pulse. And I probed it, and it's look at MOSI. 00001111. Okay? If you see this, it's some progress. And also for your IPGA leader transmitter, since you are writing an enable signal manually, right? So you put it down, and after the transmission, you put it up. We did it in the code. Let me just download this guy. So click it, download it. I don't know why it's not downloading, but there might be a example code. Let me see. Yes, we do have it in the lecture. Oh, that's why. Auto internet. Okay. So I just lost that page as well. It's back. All right, this one. This is the leader transmitter code. So that we are only looking at the big picture of it. Keep in mind. Don't dive into the nitty gritties. It's just so much stuff in there. So we just look at the big picture. So what is this really doing here? So first you need a clock. This is a liter transmitter, so it defines a clock, right? ICK. So you are doing a clock division, counting that 100 megahertz clock to, I count it to 100K, and then I flip it. So eventually it's slowing the clock down a lot, which is fine because you can even use a switch to clock it for SPI. Because that's a liter transmitter. Whatever clock you want to define, it defines it. Okay? So the follower is going to follow it. Doesn't matter how slow that is. Can you imagine SPI manually clock? Okay. But this is still way faster in your hand. Okay. But I slow it down, just trying to look at the signals and not overwhelming the UART as well. And eventually that worked. We can change it back to a faster rate and until the UART is not functioning anymore. But now I think this is fine. Let's just use this count. So it's 100K. The 100 megahertz is counting to 100K, and I calculated. Eventually, it's making a 500 hertz transmission for SPI. I'm sorry for that, but SPI should be doing like 2 megahertz, right? But not 500 hertz. Okay, so that's the clock you generated, and then at the negative edge, negative edge or falling edge of the clock, it's putting everything onto MOSI. See? Data with the index is being put on MOSI. MOSI is just the one wire, it's serial. Okay? So the data with the index, it's a parallel data from the input of the SPI. It's taking out one by one and place it on MOSI. So you are doing a parallel to serial conversion right now. That's the transmission. And that happens at the falling edge. Keep in mind. So that happens at the falling edge of the SCK. Okay, that's a big picture. We just need to know this, but nothing else. Oh, there's another one we need to know, which is the busy. Okay, see, whenever it's done, busy becomes 0. Oh, definitely the enable pin becomes 1. So we enable it by pulling it down, and whenever it's done, we pull it up. That is what we are seeing here. The link. Okay, see, SS, we pull it down to 0 whenever the data transmission is completed. We pull it up. Did we do that in your Verilog? Yes, we did. Begin, start the transmission. SS becomes 0. Pull it down. Whenever it's completed, pull it up. Okay, and we are seeing the same thing as we program. That's for SS. For MOSI, what we did to MOSI, whenever it's doing the transmission, it's gonna stay at here, right? It's just doing until it finishes all the 8 data points. Then it moves to stop. So the 8 data points will be placed on MOSI one by one, starting from MSB or LSB. Which is being sent first? MSB or LSB?
It's the most significant bit.
MSB, why? Because indexing is subtracting 1.
Yeah.
Okay? So index originally is what? 8.
Yeah.
So it's starting from index, from the MSB, which is 7, right? It's 8 minus 1. So every time it placed 1 bit onto MOSI, and index minus 1 is moving to 6. And then 5 and 4, eventually 0 as the last one. So it's sending MSB first. Okay? And this is how the liter transmitter works. And we have the constant. Okay? So this is the constant to be sent. Which one is being sent first?
0.
0, yeah? So this 0, right? This 0 will be sent first. And then the following zeros and then 1s, right? So that is why we are seeing this. 4 zeros and 4 1s. How do we know these are 4 zeros and 4 1s? It's just a straight line, right? How do we know that?
It's just the change in voltage. Like you can see like where the zero voltages and over.
I know, but who defines it?
I guess we do. Or,
Yeah, where?
in, I guess, 'cause I guess the board does 1 volt, so
ICK, right?
yeah.
It only send it at floating edge of the ICK. Since we wrote it that way in Verilog.
Yeah.
So the floating edge of the ICK, we take that in. We placed it onto MOSI. And that's why here, see? Here, MOSI shows a 0, right? So these are outputs from the IPGA. Keep that in mind. So floating edge, floating edge, floating edge, floating edge, floating edge. So at the floating edge, it changes. Does that make sense? Why the floating edge here, it changes from 0 to 1? Why at the floating edge here, it changes from 0 to 1? Not during the high, not during the low, not during the rising edge, but at the floating edge, this changes from 0 to 1. Why?
Isn't that how you said it? Said it's a negative edge?
Yeah, that's what we did, right? Remember, it's the negative edge of the ICK. We placed it onto a MOSI, right? That's how that works. That we programmed it that way in Verilog. So this MOSI data change is synchronized with ICK's floating edge. Okay? This is everything provided by the IPGA board. Now what do we need to do? We need to take it into the Arduino, right? How do we do that? So these 3 pins are shorted to certain digital pins of the Arduino, right?
Yeah.
And is that a smart way to do things by taking the data into the IPGA, into the Arduino at the floating edge? Because at the floating edge, IPGA placed the data onto MOSI.
Yeah.
Okay, so I'm just using Arduino to sense that floating edge and take it in.
Yeah.
And why do we have to rush so much? Because the next data won't be placed on MOSI until the next floating edge. And in between the 2 floating edges, what do you have in the middle? A rising edge.
Yeah.
Is the data changing during the rising edge? No, because it only changes at the floating edge. So you do have a rising edge in the middle that gives the chance to take the data in, to sample the data, and which will be in the middle of the data, which is the most stable one, right in the middle of the digital pin, of the digital data. So that's the best chance to sample it. So when you are writing your C code in Arduino, you just sample it during the rising edge of the ICK. How can you know that? ICK is shorted to one of the digital pins of Arduino, so Arduino can sense it. So now the question is, how do you sense that rising edge? Okay, just C code, right? That's a different problem. We just request it. We need this. Then we think about the problem later. How do we figure that out later? Okay, so now we need to sense the rising edge. Make sense?
Yeah.
However, there are so many rising edges. ICK has rising edges anywhere, everywhere. It's not stopping. How do you know that this rising edge is the rising edge you need to use, but not this one? It shouldn't be this one, right? Because the SS is not enabled. It shouldn't sample anything here because SS is 1. It's not a valid data. But however, how do you know it? Arduino is not able to tell. It's just a rising edge. There's no other differences.
Yes, because you do SS is not.
Yeah, so SS is another one, right?
Yeah.
You do an if statement. So if SS is 0, then you start doing that. Otherwise, don't do it. Okay. Yeah, that's the main idea behind the scene. So now let's look at the C code. It's really simple. Take a look at it, see if this makes sense. So the testing pin over here, you can disregard these 2 pins for now. Pin 11, you can just disregard it. I'm going to explain to you why I have to put these 2 lines over here. So now, let's go through this really quick, and then we go come back and explain things in details. Okay. So SS pin, definitely it's reading SS from IPGA. Now it makes sense, right? We're going to read it, we're going to sense it. Whenever it's 0, we do something, right? Okay. So So if statement over here until here is a very popular edge detection C code for Arduino. It's just detecting the last state if it's different, and so it's edge detection for the SS. So whenever the SS pin got changed, and then if the current state is low, see what I mean? So it's the edge detection for the SS pin. It has to change in order to trigger that if statement, okay? And it can change at the rising edge as well, because comparing the last state to the current state, it changes, which means it could be a falling edge, could be the rising edge, changes. So now how do you determine it's a falling edge for the changes, for two changes? Because the if statement is only able to detect the changes, okay? Only get into the if statement whenever it changes. And now it could change at the rising edge or the falling edge. So how do you determine that it's at the falling edge instead of the rising edge?
I guess you can do like a state.
Mhm.
Basically detecting what the previous state was and comparing it to the current state.
You only need to look at the current one, right? So it is like when it changes, get into the if statement, okay, and do another if statement. If the current state is 0, it changes and the current state is 0, which means it changed from 1 to 0. Okay? So it's a falling edge. Make sense?
Yeah.
Okay, that's what I did over here. It changes, it's different from the last state, and now it's low. Then we start doing something. Okay? So for here, I'm doing a for loop to take in 7 data bits, and here's the last data bit. I'm going to show you why I have to do that, and then that's it, it's done. So now look at this if statement. It's taking 7 data points. What is this doing? It's a while loop, it's a permanent loop. So I'm looking at SDK pin. Remember, we are detecting what? Rising edge of the SDK. So we are taking the data at the rising edge. So whenever SDK is low, we just hold there. It's a permanent while loop. Whenever SDK is low, which is right before that rising edge, we don't do anything. Just wait there. Just wait. It's holding there. It's holding there. The while loop. Holding here. Okay? It's like coming back and forth. Keep reading. Keep reading. Still 0. Wait and reading. Wait. Until it reaches 1, which is the rising edge. SDK becomes 1, it's the rising edge. It get out from this while loop and execute the next one. So what is the next one? For example, you are receiving the first data point. Your data, the data eventually, the byte you are going to receive is getting was initialized as a 0, okay? Was initialized as 0. The way you receive data one by one and then put it into a data byte over here is to OR it with data and then shift it to the left by 1 bit. Let's do on the paper. So that's the original data, right? Initialized at 0, all zeros. And digital read, it's gonna be either low or high. It's just 1, is either 1 or 0. However, these are being saved in the byte, even though it's just 0 or 1. So for example, it's a 1. That's what you just read. Okay? You OR it, it becomes this. You OR it, right? It's OR logic. And then you shift it to the left by 1. So MSB, right? The first one received is the MSB. However, it's being shifted to the left by 1, but eventually it will be shifted to the left by 7 times and will become MSB of the whole data, right? But now we just have to OR it and then shift it. And next time we got another data. Okay, another data, OR it one more time. It becomes this. right? And shift to the left by 1, you are getting this. So this is the to receive the data. Keep doing this, you are ORing the LSB and putting the data to the LSB and then shift it. So eventually you are getting all the 8 data points, or the 7 actually. Why? Because every time you receive it, you OR it, and then you shift it to the left. So the last time you receive the 7th bit, it's also getting shifted. All right? You don't want to do 8 because eventually you got 8 bits. Your data is getting shifted to the left by 1 bit. It's not a final data anymore. You just want to do it for 7 times. And you want to do the 8th time outside of the loop and not shifting anything because the data is ready. Why do you have to shift it one more time? Make sense? Okay? So eventually you have, for example, you got this, right? That's the 7th. After the 7th shift, you got this. You just have to do the last one outside of the loop and do another OR logic, or it, not shifting anymore. OR it, done. You got this as the last data point, right? OR it, done. Okay, don't shift. That's why I have to keep it outside of the loop. So after doing that, you are able to store all the 8 data points into this data byte, and you can serial print. People have worried about buffering. For example, even though I made it super slow, like 500 hertz, if it's running faster, way faster than 500 hertz, it's probably still fine. We have a technique called double buffering. We're going to learn that in microcontrollers in the fall. However, the serial port of Arduino in the chip, they did some buffering circuit in there. So you are actually not losing your data. Eventually, the serial communication will be the bottleneck, but it will be able to continuous data points being saved in the buffer instead of like just randomly keeping one and dropping a several. No, it's actually receive several continuously and save in the buffer, and then doing the serial communication, even though it's keep receiving really at the way higher rate, but these ones will be dropped. It's gonna buffer a certain amount of a number of data points and then send it, and dropping these ones after that, and then receiving another batch of data. Okay? Instead of randomly picking up one by one, dropping ones in the middle. It has some buffering strategy and mechanism inside the chip. So we should be fine. You don't have to worry about the buffering. It's not a microcontroller class. Don't want to dig too deep into C programming. Okay. So eventually, just print it. Don't worry about that. Just print it. It's able to buffer your data. For our case, it's probably different. For our case, our serial is waiting.
I mean, it works.
Yeah, it works. It's okay. Yeah. Okay, so that's your C language, C program. And now let's come back to these points, to these 2 points. These 2 points. Why do I want to plug 2 lines into these two spots? It's for debugging purposes. Okay? So what you are going to see on your oscilloscope is a little pulse, because whenever it enters this if statement, it sends it high, and after it executes and finishes all the data transmission, it put it down to low. You can expect a little pulse on the oscilloscope, which will make you very happy and comfortable, because you know everything inside this piece of code has been executed. And you can even measure it, how long it took to finish all the code over here. It's a really important technique to be used, even though we don't have an interrupt over here. But whenever you are looking at the interrupt, you know, sometimes you have to consider like racing. Your interrupt is usually being executed super fast, and whatever you put in the interrupt shouldn't be longer than the interrupt itself. So how do you detect that? How do you measure it? So almost all the time we have to plug all these little pulses into the piece of code in order to measure how long it took to finish all the instructions. All right, so it's a debugging tool. Okay, it's a pin number 11. It's not shorted to the IPGA. It's basically just the output from the Arduino board, and you directly probe it to the oscilloscope. That's the pin 11. Whenever it enters it, I send it high. And whenever it finishes it, I put it down to low. Okay? So I know it works. I know it enters it. All right. And also you can tell that this piece of data is not being sampled. Because you can see here is low, right? And also enable is high. So it's disabled. Even though you have a rising edge here, it's not sampling anything. Nope. It's not data. So for data points, it's only from this rising edge to this falling edge. That's being the period that is enabled as exactly 0.0001111. Okay? And after you finish this one, you got a partial credits for the digital communication part, right? Make a snapshot, put in the report, at least you are making some progress. And then you have your soldered PCB like this. You make the connections, you send the analog voltage out to pin 1, and you change this constant number back to the XADC's data. Okay? And you should be able to see, oh, one more thing I skipped. So whenever you are sending a constant data, you can see it from the oscilloscope, and also you want to look at it from the Arduino IDE. That's the way you verify it, because it's being received by Arduino, and it should be able to send it through UART.
So first is the conclusion. Okay, it worked, and shows the same thing. So which means our software works.
You see here, this one has been changed from the testing pin to the real data output. Keep in mind, it's an analog data output. Okay.
I'm gonna keep doing this.
So I'm
and I'll let you take a look at my Arduino acquisition,
and it shows
the same thing. So which means our software.
Make sense?
Yeah.
So it's displaying the analog data, but this is not an analog output. This is a digital device. So it's this digitized by the ADC and being received by the SPI, and SPI send it serially to Arduino, and Arduino send it to your USB.
Okay.
So compared to the analog, it shows the same waveform. It works.
Nice. Yeah, because it's basically taking in the binary value, right, and then converting that to like
Yes.
a
Yes.
number, and then okay.
Yes. It's all provided, open source. Didn't hide anything from you guys. It's just all there. So I think it's reasonable to get everything finished today, right? You got a team. It's not even individual work. It's just a team. So you can have someone do the soldering, someone do the constant value digitizing, right? Digitization. You can have someone work on the oscilloscope, trying to show the waveforms, making snapshots, writing the report. It's a reasonable workload. All right. Any questions on this?
The new photodiodes, are they just in your lab?
Photodiode, yes. I'll give you the photodiode. I'll give you the diodes as well. These ones, 1004, right? And these ones. Anything else you need? That's it.
Okay.
Wires. You still have time. You want to start working on it right now?
I'd love to.
Yeah.
That'd be great.
Okay, it's your choice.
Actually, for the report, what exactly are you looking for? Do you just want screenshots of like every major step?
Yeah,
and
yeah.
Explanation.
Video demos. will be nice.
Video?
Yeah.
Almost?
Mhm.
Okay.
Yeah, just show the same thing, it works, right? So if you can use a flashlight instead of turning on the light in the room.
Right.
You just use the flashlight to show the pulses, and it should show the same thing over there at the same time.
Okay, I just thought we want something similar to the Ian Taylor's as well, where there's like explanation of the code and the connections that we make.
No.
Just the demonstrations.
Yeah,
Okay.
yeah. Yeah, actually the ones I saw more issues of using forward transmitter, which is in Taylor's example. I'm gonna show you here why it's a more serious problem than I thought. This one, right? So it was a forward transmitter, and I did everything, whatever she did, and there will be like clock synchronization problems, a tricky problem first. However, I was able to, if I change the voltage down to 0, I was able to see a 0 output. If I change the output to 1 volt, I was able to see a 255. Okay? And then I disconnect the data output from the XADC with my SPI. So there's no connection, nothing. ADC is not doing anything with the SPI. And then I was trying to change the voltage. It shows the same results. I was like, I'm not going to do this anymore. So I'm going to go back and recreate Taylor's work. I'm kidding.
Well, thank you so much.
Yeah, no, not a problem. And another thing, another example from Ian's. So actually, so this work came from Ian Mason's idea, but eventually I also found a lot of issues from their code and examples. So eventually, the results they did was actually not really reflecting the analog outputs. But it's also a contribution. It's good. It's just not perfect. It has a lot of issues. So they used the interrupt to do the data acquisition, which didn't work. So we have to look at the timing. I mean, following the rising and falling edges, like what I told you guys to do. Okay. But they were also trying to do a soft SPI. Just had some issues. I mean, they had a limited amount of time during the final projects. It's still a great work, just little issues. Okay, so you don't have to refer to their reports. Just follow mine, and it should work. Okay, I'm gonna find the dials and everything and the components for you guys. You can wait here for a few minutes. I'm gonna grab the parts for you. Any other parts you need?
I'm good.
You're good. Okay, good.